Okay, so we are completing this proof right here. We're going to do proof of this first theorem. F and G are integrable. F is less than or equal to G on AB. And the claim is that the integral of F is less than or equal to the integral of G. Okay, so for the first step, notice that for H, which is going to be defined to be G minus F, we have that number one, H is integrable, and it's integrable. Remember, we have we've got this theorem right here that tells us that scalar multiples of integrable functions are integrable, and the sum of functions, integrable functions, is integrable. Okay, so H is integrable, number one. Number two, H is greater than or equal to 0 on AB. And we want to show, so our goal is to prove that the integral of H is bigger than or equal to 0. Because this is equivalent to proving that the integral of F is less than or equal to the integral of G. Okay, so now we know that H is integrable. This means that our upper integral is equal to our lower integral, right? And if we want to show that this integral is greater than or equal to 0, all we have to do is show that our lower Darboux integral is greater than or equal to 0. So it suffices to show that our lower Darboux integral is greater than or equal to 0. So fix a partition P. Then, well, let's see here. How would we show that the lower, if we want to show that the lower is greater than or equal to 0, we could also show that the upper is greater than or equal to 0. Let's see here. Well, the lower, let's look at our lower sum. Not F, I want H. This is going to be equal to the sum of the infimum of H of X over tk plus 1 times tk plus 1 minus tk. Okay, k equals 0 to n minus 1. Okay, but if H is greater than or equal to 0, that means that the infimum is always going to be greater than or equal to 0. Okay, so this is always greater than or equal to 0. And of course, tk plus 1 is greater than or equal to tk. So we can just say that LH of P is greater than or equal to 0. So for all P, our lower Darboux sum is greater than or equal to 0. Now, since the lower integral is equal to the supremum of the set of all lower sums, and 0 is a lower bound for this set, L of H has to be bigger than or equal to 0. But remember, L of H is our integral because H is integrable. Okay, go. So that wasn't that bad. Now let's show that if g is continuous, if g is non-negative, and if the integral of g is equal to 0, then g is identically equal to 0. Okay. So here, what we're saying is that if g is continuous, so we need another one. So let's do here, hypothesis. G goes from AB to R. G is continuous. So if G is continuous, if G is non-negative, so G is greater than or equal to 0 on AB. And if the integral of G is equal to 0, so the integral of G is equal to 0, our claim is that G is identically equal to 0 on AB. In other words, for every x in AB, g of x is equal to 0. What is the... 30. Okay, so now we need to prove this. And our proof, so we have a little idea. I think we have an idea here. Proof by contradiction. Use the fact that g is continuous to get an interval on which g is greater than or equal to alpha, I guess for some positive alpha. Then this integral from a to b is going to be bigger than or equal to the integral from c to d. Got it? Got it. Okay. All right, so here's still. So since g is we say we're going to do a proof by contradiction. So we'll say suppose not. Suppose that there exists x naught in AB such that g of x naught is strictly greater than 0. Okay. Now, since g is continuous, there exists a delta greater than 0 such that for all x in AB, x minus x naught less than delta implies g of x is bigger than g of x naught over 2, which is bigger than 0. So if we were to look at a picture, basically what we're saying is if here's x naught, and if at some point g of x naught is bigger than 0, we can use epsilon to be g of x naught over 2, and there exists a delta where everyone within all of the points within delta units of x naught are sent to within epsilon units of g of x naught, right? So that means that all of these points have to be somewhere in this region here. So the image of these points that are close to x naught has to be at least as big as g of x naught over 2. Okay. So what we're going to do is we're going to consider the partition. So we'll say P equals, so we'll have A, and then I want x naught minus delta, and I want x naught plus delta, and I want B. Okay, so here's B and here's A. I now have my subintervals. So that's my first subinterval, this is my second subinterval, and this is my third subinterval. Okay. Now the integral, so the integral from a to b of g of x dx is bigger than or equal to the integral from c to d of, and the c to d is really what I want is x naught minus delta to x naught plus delta. G of x dx. Why? Because we can consider the function h of x, which is going to be defined as 0 if x minus x naught is bigger than or equal to delta, and g of x if x minus x naught is less than delta. Okay? So what I'm doing is I'm saying let's compare g, right? Then g with this h. Then the integral from a to b of h is equal to the integral from, where we have the integral from x naught minus delta to x naught plus delta of g of x dx, right? And also, this integral is going to be less than or equal to the integral of g of x dx from a to b, because h is less than or equal to g. Okay. But now this integral is going to be at least so let's see here. Let me add a page afterwards. Okay. So the integral from x naught minus delta, x naught plus delta is of g of x dx is going to be at least as big as the integral x naught minus delta, x naught plus delta, g of x naught over 2. Which, remember, that's just a constant, so we can pull it out. Right, and we would just get, that would be 2 delta times g of x naught over 2, g of x naught times delta, which is strictly greater than 0. Okay, so we have that the integral of g of x from a to b, g of x dx, which is bigger than or equal to the integral from a to b of, sorry, this would be x naught minus delta, x naught plus delta of g of x dx, strictly greater than 0. But remember, by hypothesis, this integral was equal to 0. So we get a contradiction. Okay. All right, so we did that. Now, we've got our last theorem here. And this is a theorem, that is saying that the absolute value of the integral from a to b of f is less than or equal to the integral of the absolute value. Okay. So for the proof here, so it looks like we can go ahead and set up our hypothesis. So let's see here. So if f is integrable, then the absolute value of f is integrable. So for hypothesis, let's just put that f from ab to r is integrable. And our claim is that the absolute value of f is integrable. And the integral of the absolute value of f is less than or equal to, wait, it should be the other way around, greater than or equal to. Is greater than or equal to the absolute value of f. Okay. And now let's look at the proof. Okay. So for the proof, what do we have here? So the first thing we need to do is we need to show that the absolute value of f is integrable. And how are we going to do that? If f is integrable, then use part 1 of the last theorem. Okay. So it looks like to do this, we're going to use theorem 32.5, which states that we want to look at the epsilon. Copy, just so we can remember. Okay, so we have our lemma here, which is theorem 32.5. Okay. So we'll say fix epsilon greater than 0. I'm going to show that there's this a partition such that the upper minus the lower is less than epsilon. Okay. Now, in order to do this, we need to use the key fact, which is that, and this is an exercise. So from exercise 33.6, so this may be in your homework. You should do this at home. We have that the supremum of the absolute value of f minus the infimum of the absolute value of f is going to be less than or equal to the supremum of f minus the infimum of f. So we can do this, and this is x and s. Okay, so this is a fact that we can use. Okay, so once we know this, then our lower, so say for any partition P, the difference between the upper sums and the lower sums of absolute value of f compared to the difference between the upper sum and the lower sum of just regular f, right, satisfies this relationship. Okay, so since f is integrable, there exists a p such that the difference in the sums here is less than epsilon, and use that partition for so thus the same is true for the absolute value of f. Okay. And so now that we know that the absolute value of f is integrable, then we can say that f is always less than or equal to absolute value of f. So the integral of f is less than or equal to the integral of the absolute value of f, right? And since f is bigger than or equal to negative absolute value of f, that means that the integral of f is bigger than or equal to negative integral of absolute value of f. So that means that the integral of f is in between the absolute value and minus the integral of the absolute value. So the absolute value of the integral has to be less than the integral of the absolute value. Okay. And the last thing is make sure that you read about piecewise monotone functions and piecewise continuous functions and how to integrate them on page 286. So this is 286, and 287 has also something that's very interesting, which is the intermediate value theorem for integrals. So the IVT for integrals is also very helpful.